So I gave my consent to being filmed. Would you give me your consent to being filmed? At least just take a picture. Is it okay?
We don't have to smile. Yeah.
You have to smile. Otherwise, it's thank you. Okay, I can take another picture at the end. So then we see.
I'm afraid you've gone.
Maybe my adapter is
But
not. Get a couple of pairs.
in a twofold way.
Maybe we have sorry to use another adapter.
Well,
It seems it's turning on and off. Sorry.
So my experience is that the adapters work randomly with those.
Yeah.
okay.
Does anyone have
So
an
maybe
adapter?
we should skip.
Or
Yeah, that's
HDMI or
Okay, maybe
an obstacle.
maybe I can use mine.
But then
no, we can use it. We just need to take
that
another
will
adapter.
exclude online.
No, I can bring another adapter, and I hope it will work because it's like turning on and off. I
Okay.
1 minute.
All
But
right.
maybe I introduce the speaker, and it will start start. I'll be back in a minute for sure. Okay, so I have to take an adapter. It is our pleasure and my pleasure to introduce Nikita Nekrasov, whose name is widely known. He's from Stony Brook Simon Center for Geometry and Physics. Yeah, you might have heard of Nekrasov partition functions. So this is his invention. He received various prizes in mathematical physics, Hermann White Prize, and other ones. So we are just very happy to have him. And let me already announce that the talk will be continued tomorrow at 2:15. So please book your calendar, and I hope that we also meet tomorrow. And I think I can start, and I will be back in 1 minute with another.
Okay, thank you very much. So the title, one of the titles of my talk is relativistic hydrodynamics as an intersection problem. So, well, the equations describing the fluid dynamics are pretty old. So they about, let's say, more than 350 years old. So they are not Euler wrote the first types of equations which you will probably see. So this is the most studied mathematical equation, which is not most interesting physically. This is the equation for the incompressible fluid moving in three dimensions. So V is the velocity vector field, and P is a scalar function, the pressure per unit volume, so to speak, which is determined from these equations. So it's not an independent quantity. You apply the divergence to the first equation, and that gives you an equation determining the pressure. So in a sense, this is a highly non-local evolutionary system, because so P can be expressed in terms of the velocity vector field through the Poisson equation. Now, since So these equations are written in a way which is kind of non-invariant. So it will only make sense in the domain in Euclidean space, and implicitly flat metric is used. So Euclidean.
Nikita, if you don't mind, you can switch to.
Okay, sorry. Yes. Yes. Okay, let's switch back.
Just to use our so.
Okay.
You can remove this from the screen. The many displays.
Try.
Oh, yeah, perfect. Yes.
Maybe this side. Oh, okay.
Okay. All right. Yes. So my talk is based on the paper. So it cuts. Yeah, it cuts an important part. So it's a paper we posted last month with Paul Wigman, and we still continue working on it. So it's something we've been working for a few years now. The story is the following. So as I started describing, so there are famous Euler equations, and then there are the modifications involving viscosity, the Navier-Stokes equations. There are some famous prizes attached to proving some distance theorems about these equations. People study the chaotic behavior, they describe the turbulence, so on and so forth. And there is a smaller community of people who study the generalizations of these equations, describing the motion of fluids which can achieve velocities close to the speed of light. So this is something of interest in astrophysics, presumably. But also conceptually, you would like to be able to understand how the fluid is moving in general gravitational backgrounds, let's say near a black hole, or in some curve, in general curve metric. And of course, so all your equations, the way I wrote them, use Euclidean structure, so they're not good for that. So we would like to be able to write the equations not just covariantly. You can read those in the textbook by, let's say, Landau-Lifschitz, and they were developed in the last century by many people, starting with, I say, Lichnerowicz, and then developed by Carter and his pupils and his collaborators. So people studied these equations for a long time, including my collaborator Paul Wigman, who developed the versions of these equations describing the motion of anomalous fluids where the particle creation takes place. And at some point, he visited me at Simon Center. He started telling me about these equations, and I recognized some structure in the way these equations are written, which I think is more important than the equations themselves. So so I believe this reformulation which I'm suggesting, which we will be presenting, is worth thinking about, and it might be a useful angle at not only at hydrodynamics but other equations, and also because of the connection of intersection theory to certain problems in string theory, in mathematical versions of string theory. There might be interesting developments in this domain. So let me start by reassuring you that lots of interesting ordinary and partial differential equations we know and love in mathematical physics actually can be cast in the form of an intersection problem. So this is a painting by Bragg, as you see lots of intersections, so it's a lot of geometry. And so this is a classical problem in algebraic geometry going back to 19th century, so not as old as Euler equation, to find, let's say, a number of lines passing through 2 points on the plane, and then quadrics going through 5 points, and all kinds of incidence problems. You have some equations, they describe some geometric structures, and you want to find the number of solutions of this equation. So this is the counting number of intersections of some varieties. So what I want to remind you, in case you haven't thought about this, is that actually many PDEs can be also reformulated as interesting intersection questions. And this becomes especially interesting in case where the partial differential equations describe evolutionary systems, but in a form which is covariant with respect to the space-time coordinate transformation. So they formulated not in the evolutionary form like Euler equation, when you have space and time which is completely separate, but in space-time form, like in general relativity maximum equations, for example. So yeah, there is something to the scale of this.
That's right.
Let me try to.
We go to this PDF.
You were. How this? That's I don't want to touch because, for example, this could happen. Smaller scale.
Let's just spread the application window all the way.
Sorry. Oh yes, I think that's better. That's better. Thank you.
Thank you.
Now
Oh, no, sorry.
by itself, but it's
No, slides. I'm afraid. So it will be changing slides.
It's okay. I think we just. Almost there.
Maybe I can just make it bigger like that.
Yeah, but you have to control what you're sharing, because what I see is half the screen. Oh, no, that's not. Yeah.
We're slaves of technology. Sure. Not the first to point this out. So
Well, we can change it just like.
yeah, so let's go one slide back. Yeah.
So,
Yeah, okay.
Sorry. Okay. Okay.
Excellent. So the statement which I want to make is that the covariant space-time equations of mathematical physics, they express incidence relations. Incidence relations meaning intersection, just of interesting subvarieties, specifically Lagrangian subvarieties, sometimes Lagrangian subvarieties, in some auxiliary phase space. So what is new here is that right. What is new here is that unlike the traditional approach of classical mechanics, where you have a phase space which describes the states of your classical system, like you specify coordinates and momenta, and that's your initial point which can then evolve. Here, the phase space which I'm talking about is defined in terms of processes. So the space-time histories of the system you're interested in. I call it phase space because it will have the symplectic structure, just like the traditional phase spaces have. But the role of this phase space in describing evolution is different. So the point of this phase space is the whole space-time history. And in particular, right. So well, I will be much more specific later. So usually in classical mechanics, we have the phase space describing the states, as I said, and it has symplectic form, which you can, so it's a closed non-degenerate 2 form, which you can bring to the canonical form. let us say, find local coordinates, that are coordinates in which it has this form GPTQ, many P's and as many Q's. And the interesting submanifolds in the phase space, the ones which kind of describe the good initial conditions for the evolutionary system, are formed by Lagrangian submanifolds. So these are maximal isotropic submanifolds with respect to the symplectic form. So these are the submanifolds on which the restriction of symplectic form vanishes, and they have the maximal dimension, which is the half of the total dimension. So locally, the equation, if you solve the equation omega, the restriction of omega is equal to 0, you can solve this by expressing the momenta, the p in terms of q, as derivatives of some function. This function is called the generating function of the Lagrangian submanifold, and also it's called the symplectic potential, or it can also be called the Hamilton-Jacobi potential, because this is the function you study in Hamilton-Jacobi equations. So the Hamilton equations describe evolutions of points in phase space, and Hamilton-Jacobi equations describe evolutions of Lagrangian submanifolds.
Sorry, we're still fighting with
Okay, Zoom
technicalities. It's not being shared, so like there are close to 20 people outside. So I can hear your lovely voice, but other than that,
It seems it felt out.
Well, this is basically a review of symplectic geometry, except for one important statement which hasn't been substantiated. But nothing has been lost. Just while we wait, I'll just remind you that the Lagrangian submanifolds are quasiclassical analogs of states in quantum mechanics. So the symplectic potential S is what you see when you look for the WQB approximations to wave functions. Typically, they have the form exponential of I times this function S divided by H bar. So Lagrangians are like wave functions. And so Hamilton-Jacobi equation is the quasi-classical limit of Schrödinger equation. Now there are less familiar submanifolds called coisotropic. So Lagrangians were isotropic. There are kind of dual guys which are coisotropic submanifolds. So these are things which you can describe by the so-called first-class constraints. So if you locally describe some manifold by some equations, you can compute the Poisson brackets of those functions which describe those, provides these equations. And so if these Poisson brackets vanish where the functions themselves vanish, then we call these equations first-class constraints, and the submanifold they describe is the coisotropic. So it makes this condition can be formulated in cases where you have Poisson structure, but not the symplectic one. And so these submanifolds have dimension which is bounded below by half of the dimension of the phase space. Now, okay, so this is some reminder. Let me give you an example. So I mentioned the Hamilton equations. So invariantly, the Hamilton equations, given the Hamiltonian, which is the function of the symplectic manifold, have this form. So you take the derivative of the function, you get one form. You apply the symplectic form, the inverse of that, you get the vector field. So that's the Hamilton equation. And of course, you read in textbooks that these equations, so they describe a flow, and the trajectories, the integral trajectories for this flow are the critical points of the action functional. So the action functional is written, so it's a functional on the space of parametrized paths. So the maps of an interval or a line to your symplectic manifold M, and this functional consists of has two parts, and that's the key point in this intersection problem interpretation. The first term is the integral of the antiderivative of the symplectic form. It is a very well publicized story that this is, of course, ill-defined in general. It's multi-valued. All that is true, but it doesn't stop us from writing the relational principle. So it's the integral of PDQ. It's a very canonical term. It doesn't depend on the parameterization. So if I replace the path by the path which has the same image but different parameterization, the first term doesn't change. The second term depends on the choice of the Hamiltonian and the choice of parameterization. So it's a very if the first term is maybe symplectic, so it only knows about symplectic structure, plus maybe a few discrete choices, the second term is very engineer-like. So it uses the actual shape of the energy function, the Hamiltonian, and the notion of time. It's very down to earth. So now I will capitalize on the fact that the action is a sum of two terms or difference of two terms, and represent the variational problem as a solution of intersection problem. So I'm looking for intersections of two submanifolds. One depends on the symplectic form omega, so it's like called L omega. Another one depends on the choice of the Hamiltonian and the time. And so its intersection will take place in some phase space P sub m. So what is P sub m? It's going to be the cotangent bundle to the space of paths. So it's an infinite dimensional manifold associated to my symplectic manifold. So the points of that space are pairs. So gamma is the path. And the rho, so rho is a choice, it's a covector field on M, the target space, which is only defined on the path. So at every point of the path, I have a choice of a covector. So it's an infinite dimensional space. Also, this rho, this covector, I also want to think of it as a one form on the domain. So my paths are maps of something one-dimensional into M. And so these dual objects are one forms on the domain and also one forms the target space. So the covectors and target space. Oops, maybe so the reason okay, so the reason I mentioned that is that the symplectic form, the canonical symplectic form of the space is well defined. So it's an integral over the timeline. It's a variation of the path and the variation of this covector. And this guy being one form, so the whole product is a one form on I. So, and I say that in this space of paths and momenta, I want to set up some intersection problem. And so my first, so I want to define two structures which I want to intersect, two submanifolds, subvarieties. So the first one, as promised, depends only on the symplectic form. And so it consists of the pairs path and covector, such that the covector is obtained from the velocity vector field using the symplectic form. So this is the equation which describes it. As you can see, it's a completely representation invariant equation and doesn't use anything except the symplectic form. So the second equation, as promised, depends on the symplectic, on the parameter. So with the choice of the time variable t and the choice of the Hamiltonian. And so the pullback of the derivative of the Hamiltonian times the differential of the parameter dt is equal to rho. So that's the second. Now I claim that both of these subvarieties L omega and LH dt are Lagrangian submanifolds of this infinite dimensional cotangent to the space of paths. Now, if I equate, so I look for the points of intersection, then it's elementary, of course, that you will get back the Hamilton equations. The reason why I went to this trouble to reformulate something simple, so sufficiently simple, as something rather complicated, is that that complicated formulation admits generalizations and further generalizations to the case where the simple thing like Hamilton equations are no longer available, or they don't follow from a symplectic structure. So getting closer to our story, to the story of Euler equations, we're not always lucky. We're not always that lucky that the dynamical system we study comes with the symplectic form on some space of states. Or maybe it comes with a symplectic form, but it's very, very painful to get it. So more often than not, we have a Poisson structure. Yes.
I have a question.
Yes.
I didn't get it. So how do you get the Hamiltonian equation from this intersection? Do you have intersection, and what do you calculate there?
So if you just say that you look for the points gamma rho, which belongs both to this submanifold and to this submanifold.
Yeah.
So you equate them.
Yes.
So what you will get that gamma dot omega times gamma dot is equal to th. So you'll get back the Hamilton equation. So what you will get will be that the trajectory, this path, which is gamma, is the integral trajectory of the Hamilton vector field.
If there is intersection.
Yes, yes.
This is basically first order formalism, roughly speaking, isn't it?
It is the first order
Yeah.
formalism.
On the first bundle.
Yes, yes, yes.
Yeah.
But the point is that you see, I mean, we all know this first order formalism. We all know that varying this functional gives you the Hamilton equations. The thing which I did is I surgically looked at I looked at this functional, and I say that it consists of two parts. And so each part defines actually separately meaningful submanifold in the cotangent in the space of paths. And so the intersections are the all good Hamilton equations. But you can also study the Lagrangians by themselves and the deformations, because the deformations are independent of each other. And so you can separate. I mean, I will have some jokes about it. So let me not go. All right. So now I want to generalize. Suppose that I have a Poisson manifold, so I don't have a symplectic form anymore. I have a manifold M with a Poisson bivector pi. So it obeys the Jacobi identity. This is the Jacobi identity. I can write this equation. So it's the equation says that I can still define the vector field by taking the one form, the differential of the function, and contracting it with the bivector. So the bivector is like two vectors. One vector contracts with one form, gives you scalar. The other vector remains, gives you the vector field. And so that's the kind of Poisson version of Hamilton equations. Nice. But I want to have a variational principle. And so one way to get it is to map this Poisson dynamics to the symplectic dynamics, and then I know how to get the variational principle like before. And unfortunately, there are two well-known ways of mapping Poisson dynamics to symplectic one, and both are very painful. So the first possibility is to say that, well, from general theory of Poisson structures, Poisson manifold is actually foliated by the symplectic manifolds, so-called symplectic leaves. So the Poisson structure is not invertible, but you can always find a submanifold on which will be invertible and will define the symplectic form. And moreover, so the symplectic leaves, they're locally given by the level sets of functions which Poisson commute with everything. So and therefore these functions, which are called Casimirs, they are preserved by the Poisson dynamics. So they're constants of motion anyway. So you can restrict your trajectory of your Hamilton vector field to this leaf. It will be a Hamilton vector field on the symplectic manifold. And so you can use the previous story. The second approach is to say that actually there's a kind of dual approach. Instead of restricting, you can add degrees of freedom and realize that your Poisson manifold is actually a quotient or locally a quotient of a larger symplectic manifold. So it's called symplectic cover. Now, why do I call this roots suffering? It's because in interesting cases, like the hydrodynamics, for example, these Casimir functions are extremely highly non-local functions. Nobody knows how to write them, except for a few cases which I will mention. And it's not very practical. And adding degrees of freedom means, in practice, adding infinitely many degrees of freedom. In the case of Euler equations, this is essentially going to Lagrange variables, which keep track of where the fluid particles were initially, and so working not just with the vector field, but also with the mapping of some initial positions of the fluid particles to the current position. So it's a very expensive. If you want to do it on a computer, it's very expensive. Okay, the painless option. So I just spent 4 months traveling in India. So this is the India, not in India, in actual India, but in the spiritual India. There's a school of thought called Buddhism, which says that you can actually avoid, pain if you think good enough. So the painless option to pass from Poisson dynamics to the symplectic one is to use the same symplectic manifold, the cotangent bundle to the space of paths. It is infinite dimensional, but it's kind of moderately infinite dimensional. So now the claim is that very similar equation to the equation we wrote before, except that now instead of omega on the left-hand side, I have pi on the right-hand side, turns out to be now a coisotropic submanifold. So it's a submanifold of this symplectic cotangent bundle to the space of paths, which consists of paths such that the momentum contracted with the Poisson by vector gives you the velocity, the tangent vector to the path. And the second submanifold remains the same. It's Lagrangian as before. So now intersection of this with that gives me again the Hamilton equations, but now in the situation where I have a Poisson structure. So this is the kind of the first indication that we might get formulation of an interesting problem where we have some ambient symplectic manifold, and we have a coisotropic submanifold, which is almost Lagrangian, and Lagrangian submanifold, which depends on some something like chemistry, so some sort of dynamical information, macroscopic dynamical information, like the choice of the Hamiltonian and the notion of time. So the interesting aspect of these constructions is that of course, the problem you're solving is the same problem, but now you look at it as an intersection of two structures. And so these two submanifolds, they carry different structures. They care about different things, and they carry different structures. So this is like church and state. So people can be both religious and good citizen, but so they kind of care about different things at different moments of time. So in the examples which I gave you, I had one Lagrangian submanifold which carry about the Hamiltonian, and another was Lagrangian or coisotropic, which carry about the symplectic structure. There are other examples like the study of harmonic maps, for example, where on one submanifold you will care about the conformal structure, another will care about Riemann structure. One example which is dear to my heart, and I know it's dear to hearts of some of you, is the Liouville theorem. So Liouville theorem is a partial differential equation in 2 dimensions, which describes the metrics of constant negative curvature. I drew 2 examples. Riemann surfaces with metrics of constant negative curvature. So in local isothermal coordinates, the Liouville equation is the equation on the function, on a single function, which is essentially the conformal factor. And so I claim that the solutions to Liouville equation are also intersection points of two Lagrangian submanifolds in some ambient symplectic manifold. So what are these Lagrangians and what is ambient symplectic manifold? To get there, let me remind you the construction due to Poincaré. So he found that if you define, so given the solution of this equation, if you take the holomorphic derivative of the field phi, take a square and subtract the second derivative, you get an object which is actually holomorphic. Oops. Yes. So the anti-holomorphic derivative of t vanishes as a consequence of the Wiggle equation. And if you think about the global properties of this object t, you will find out that it looks locally like a quadratic differential, but in fact it is not quite a quadratic differential. It transforms as a constant term in the second order differential operator. So second order differential operator, scalar second order differential operator is like the first order matrix differential operator, also known as a connection. And the connection, so if you, the simple thing which you can do by going to, again, first order formalism, is to map this differential operator to the SL2C connection. And if you supplement this with the operator dz bar, you'll get flat SL2C connection. So a solution of the Wiggle equation actually defines an SL2C flat connection on the Riemann surface on which we are looking for the solution of the Wiggle equation. But it's not any SL2C flat connection. Actually, it's a flat connection with real monodromy, because this original field phi was real, and that imposes certain reality conditions on what are the holonomies of the local solutions of this equation. And so geometrically solving Wiggle PDE is finding the intersection of two Lagrangian submanifolds in the complex symplectic manifold of SL2C flat connections. One is called the variety of Opers. So these are the SL2C flat connections which can be gauge transformed to the second order differential operator, like g squared plus t. And the second is the space of flat connections with in the SL2R, so real flat connections. The similar setting shows up in another problem which has recently become quite popular, so-called analytic Langlands program. So there people look for the eigenfunctions of certain Hamiltonians, certain quantum Hamiltonians, so differential operators acting on functions on modulus basis of flat SU2 connections. And the spectra of those operators are described by similar intersection problem. Similarly, in many better ansatz equations stories. So it's quite abundant. So the class of examples where this intersection theory problem emerges is quite widespread. So let me now go to the. So this is the reason I mentioned is that this has further levels of refinement when these intersections can be sometimes described in a way which makes contact with the enumeration of solution, or with the integrals over the modular space of solutions of some PDEs like instantons, and so the variety of Opers, which I mentioned in the context of Wiggle theory, is a limit of some generating function of instanton counting in 4 dimensions. Let's forget about this for now and proceed with the case at point, which is the hydrodynamics. So as I mentioned on the blackboard, So we are familiar with the Euler equations for divergence-free vector fields in 3D, and they can be generalized, and they were generalized to describe the fluid motions on general orientable three manifolds endowed with the volume form. So volume form is just a three form which is not allowed to vanish. It's kind of the form which produces orientation in three manifolds. And the playground for Euler equations, for Euler equations, I'm sorry, is the group of diffeomorphisms which preserve the volume. So back in the 60s, Arnold recognized that the equations, the Euler equations, are actually the version of a spinning top equation defined on the quadrant orbit of the group of volume preserving diffeomorphisms. So just mention that. So one feature of the spinning top equation is the equation describing the. So if you take a familiar rigid body, the actual spinning top, so the body which rotates in 3 dimensions, this is a finite dimensional dynamical system defined on the Lie algebra of the group of rotations of R3, so group of SO3. So that we write these equations in terms of the angular momentum. So it's a 3-vector, and there is some equation which tells us how the angular momentum evolves in time. So the analog of the angular momentum for the fluid dynamics is the vorticity, which is the 2 form on the 3 manifold, and the Euler equations say that the time evolution of the vorticity is just the flow with respect to the vector field which fluid represents. So by itself, it's not enough because you need some equation relating the velocity and the vorticity, and so there is some linear map from V to P. P is the momentum, and omega is just Zp. So it's called the inertial map. This is the analog of the inertia tensor for the rigid body.
Is it an infinite dimensional symplectic manifold or Poisson manifold?
So the group there is a group. There is its Lie algebra. There is a dual space. That's a Poisson manifold. And as I mentioned, if you could fix the Casimirs, all the invariants, that would define the symplectic. And as I mentioned, in general, it's an impossibly hard problem, but there are special cases. There are small orbits where the vorticity is a 2 form which is concentrated on the curve. So in fact, this curve could be a knot. And in this case, we know how to specify all the Casimirs. This problem actually is in itself is a very famous, also old problem. All the Casimirs for that type of orbit are all the knot invariants. So for those people who are interested in knot invariants, the classification of knots is contained in the problem of writing the Casimirs for the volume preserving diffeomorphism. So in this case, it's kind of possible to rewrite this in terms of symplectic manifolds. So there is this Weinstein symplectic form on the space of knots. So it will describe the evolution of a knot. So the knot will kind of move in 3 dimensions. But in general, it's impossibly hard. And okay, I'll skip this Poisson formulation, which is just answering this question. This is too idealized because the interesting fluids are not incompressible. And my goal is actually to describe the relativistic fluids. They are always compressible. You cannot have an incompressible fluid in relativistic setting, partly because what is compressible and what is incompressible depends on the frame. So incompressible fluid is simply not interesting, even though there is $1 million price for that. It's not the right problem. Sometimes people who give prices, they don't think ahead. So this is a more realistic set of equations. Now we have density, which is dynamical. The vector field is now a general vector field. And in addition, there is an energy density. So now the the pressure, which is still there, and there is now density rho, the pressure is not determined by the velocity vector field itself. It depends on the internal state of the fluid. So the pressure is a function of the density and an additional variable, which is called entropy per particle. The word entropy, unfortunately, has been overpopularized and means pretty much nothing, because different people mean different things by entropy. So there is an entropy which is sometimes has a statistical origin, but it's more often than not, it's just some hidden variable which tells us that in addition to the density, which clearly determines the informs the pressure, which is the reaction of the fluid to the compression, there are additional degrees of freedom at play, which are simply transported with the fluid. So this is the equation which says that the entropy is just being transported without any additional evolution. So overall, these equations, so there are basically 5 equations for 5 unknowns. So 3 components of velocity, the density, which is a 3 form, and the function s, which I will keep calling entropy, even though I have some issues with this. So it turns out that we can reformulate these equations in a way which makes contact with spinning tops and interesting real algebras, and also reveals an unexpected symmetry, which to our knowledge has not been discussed in the, well, maybe up to except for some discrete subgroups of this group. Let me now proceed mathematically. So I'll just introduce some objects. I'll write interesting equations, and then I'll explain that these are the same equations as Euler's equations for compressible fluid. So my players will be momentum pi, so it's Greek letter pi, which is a one form valued in densities. So it's a one form on the 3-manifold tensor 3 form. So it's the components of this one form are not scalars but pseudoscalars. And 2 densities, rho 1 and rho 2. Not 1 but 2 densities. Now this is the so this triple pi rho 1 rho 2 is actually an element of a dual space to the Lie algebra, which consists of the vector fields on the 3-manifold and 2 functions. So these functions are actually chemical potentials in physics language, and the vector field V is a vector field, which describes the fluid motion. Now, there is something called the equation of state. So there is some relation between the velocity and chemical potentials and the momentum pi and densities, which typically follows from some function h called Hamiltonian. And for the conventional non-relativistic fluid, this functional h is a sum of kinetic term, which is pi squared times density. I'm sorry, this should be b, and some potential term, which depends on the ratio of 2 densities, which is integrate versus the density. So this represents some internal degrees of freedom. The beauty of this formulation is that Euler's equations are pretty simple. So they say 2 things: that both densities are transported geometrically, and then the momentum, in addition to the geometric transport, is also shifted by something proportional to the derivatives of the chemical potentials and densities. So these equations, instead of writing them, I could have just said that this is a spinning top equation written for the group, which is the group of diffeomorphisms of the 3-manifold, all diffeomorphisms, semi-direct product with vector valued functions on the 3-manifold. So this is the Lie algebra. So the Lie algebra consists of a pair of vector field and two functions, and the commutator is the commutator of the vector fields as vector fields, and then the vector fields act on functions just by derivatives. So functions commute, but vector fields act on functions. So the resulting Lie algebra is a non-trivial extension of vector fields by functions. So it was observed in 82 by Sergei Novikov that Euler equations for compressible fluid are the Euler-Poincare top for this infinite-dimensional group. A bigger group, but still there's a spinning top equations. Now the entropy, so this entropy function which Euler had and Laplace had, and some people, Laplace, so all great names contributed to those equations. So this entropy is actually physically we should think of it as of the ratio of two densities. So when we talk about the compressible fluid, the equations secretly describe the motion of a two-component fluid, two-species fluid, of which one component has inertia. So the energy for one component contains the traditional kinetic term. The second component has no inertia. It is just being carried by the first. So it's more like a dye you put in water, but the compressibility of the inertial component depends on the presence of the second. So it's an interesting interacting system. And so now, yes. So now my time is almost up. So I will just formulate the four-dimensional equations, which are so the relativistic version of the Euler equations of compressible fluid. Maybe tomorrow I will elaborate on that. So the equations themselves, in various forms, which are typically very, very complicated, were written by Lichnerowicz in 1967. So it's just 1 year after Arnold identified incompressible Euler equations with the spinning top, and Carter in 88, which is like 6 years after Novikov interpreted compressible Euler equations as a spinning top for a different group. And they were, of course, developed by many, many people. But I will not repeat the painful story of how these equations are written. I just want to present the answer in the form which I already commented on. So the starting point will be the smooth form manifold. So it's our spacetime. Although it could also be a compact K3 surface. So at this point, it could be any smooth manifold. I want to associate with the form manifold M, the infinite-dimensional symplectic manifold, which you should think of some kind of analog of the cotangent bundle to the space of paths. But paths where? I will not tell you yet. In fact, this manifold is much simpler than the space of paths. So it's just the space of one forms, so 0 forms, 1 forms, 3 forms, and 4 forms. So all differential forms except for the middle ones, except for the 2 forms. Why 2 forms are omitted? Well, because I'm writing the simplest possible symplectic form on this manifold. It's a vector space. It's a symplectic vector space. And I'm writing the simplest possible symplectic form you can think of, which pairs 0 forms with 4 forms, 1 forms with 3 forms. So if I had 2 forms, I would have written the delta 2 form, wedge delta 2 form, but that vanished. This vanishes. So there is an interesting, curious symplectic manifold one can study, which is this space plus 2 forms valued in Grassmann numbers. So inverted parity 2 forms. That would be an interesting symplectic manifold. I don't know what's the role of that manifold is in fluid dynamics. Maybe there are some spinning fluids which can be described by that. But for the moment, let's just be simple. So this is something very simple, okay? This can be made slightly more complicated by modifying the symplectic form using the so-called Chern-Simons correction. This is a two form one can write on one form on the form manifold. Something I played with in 1991. My first first student paper was on five-dimensional Chern-Simons theory. So this is what you find there. So here it's just a small correction to the Liouville form. And there are other generalizations which I will not discuss now. The claim is that the relativistic hydrodynamics, the flows describing relativistic fluids, are the intersection points of two submanifolds inside this vector, symplectic vector space. One, which would be quasitropic, it carries the only information it carries is the smooth structure of the manifold M and the symmetry which is associated to it. And the second would be Lagrangian. It depends on the metric, on the choice of the metric on them, and something I call chemistry, so some additional choices. So this quasitropic submanifold will be simply the zero level of the covariant moment map for the group of diffeomorphisms of the form manifold extended by functions. So not vector functions, but just ordinary functions. And so this group acts on my manifold. In fact, there are two interesting actions. One is simply by shifting the one form by the differential of a function. So theta is this function element of C star. And another is a kind of rotation where you shift the one form by derivative of the function times the function S, zero form, and the four form by three form which the derivative of the function. So the difference between these two, so on the nose, of course, these are two different group actions, but it turns out that when combined with diffeomorphisms, they become almost equivalent. Almost, I mean, up to measure 0.7. So associated to either of these actions, you can write the moment map. So the generators of the infinitesimal transformations associated with this group, generators in terms of symplectic form. And so there is a moment map for diffeomorphisms and a moment map for these scalar actions. So let me, for brevity, just mention the first one. So the generator of the transformations where P is shifted by one form is just D of M. This is the Gauss law, which you can recognize from Maxwell theory. And the generators of the diffeomorphisms are quadratic in the fields. So this is the lengthy formula. There are shorter versions of that. So this is the shorter version. Anyway, so I want to set this to 0. So that imposes a set of quadratic equations on my variables S, P, and nu. And so it defines some kind of a cone inside the symplectic vector space. And that's the quasitropic submanifold. I call it brain because of the later connections of string theory, but I will not talk about this today. So just this level set of these equations. Zero set of these equations. Now the second submanifold, and so the goal is to intersect this cone with another submanifold, which will be Lagrangian, and it has the generating function. For example, in the so remember. One canonical way of describing the Lagrangian submanifold is to split the coordinates on this symplectic manifold into Darboux pairs, P and Q, find some function of Q, and write that P is derivative of this function with respect to Q. So this Lagrangian submanifold in the present case is determined once you have a function of two variables, epsilon, and you have a metric on spacetime. So then out of the three form n, you can form a scalar, and the norm of this three form, and you substitute this scalar and this function s into epsilon and integrate over m against the volume form associated with the metric. So that gives you a functional of s and n, and now you can use this functional to describe the the remaining variables p and nu, and so that will give you the equation. So notice that my description so far only used differential forms. There were no vector fields, unlike the usual vector Euler equations. So there is a way to produce some vector fields from the data from these forms. So one vector field is called Landau vector field. It uses the metric. So given the three form, its Hodge dual is one form. So if I lift this index using the metric, I'll get a vector field, and I can normalize it by dividing by its norm. So the Landau vector field has a unit norm. There is another vector field which is called canonical, which was introduced by Carter, which is simply defined. So it's defined without metric. It is defined as follows: the three form n can be obtained from the four form nu by contraction with some vector field. That's vector field V. So it turns out that these vector fields are proportional to each other, so V and Landau, but this vector field V is better suited for my purposes. So I suggest I stop now and continue tomorrow. So my claim is that these are the equations. So I already described for you the equations of relativistic hydrodynamics. You might not recognize them yet, but it's already been done because I said everything. So tomorrow we will explore these equations, and I will maybe give more details and give more geometry. Thank you for your attention.
Are there some questions? Yes.
You mentioned some intersection theory. So finite dimension intersection theory is governed by some combinatorics, by Grassmannian, the Young law. And here you have infinite dimensional space. So in the cycles are other half infinites.
Right.
So what kind of intersection theory?
So this is this best slide about this. Oh, okay. So there is a now developing mathematical subject called Lagrange intersection floor theory. So this is precisely the study of intersections of infinite dimensional submanifolds inside the infinite dimensional space, and these submanifolds have dimension, which is of course infinite, but it's sort of finite amount of half dimension.
Yeah, that common.
And this is defined using, yes, precisely, so index theory. So, so this is what mathematicians, so this is kind of, maybe it's not developed, but it's now in the mathematical reality. And the intersection theory, which I'm proposing, is still far from that because so one of my submanifolds is Lagrangian, so it is exactly half-dimensional. But second one is coisotropic, and coisotropic means that it could be of higher dimension than so it could be higher than half-dimensional. There is some measure how much the coisotropic submanifold differs from a Lagrange. So I had a few slides about that. Unfortunately, in this case, this coisotropic submanifold, which is the zero-level set of the moment map, how much it differs from Lagrangian is measured by the quotient. So the quotient, which is also known as symplectic quotient. So it's a symplectic quotient of my vector space by the group of diffeomorphisms and the functions. This is a space which has zero functional dimension because the way it was some numerology which I didn't stress, it was important. And if you think about the functional dimension of these spaces, so 0 forms have dimension 1, 1 forms have dimension 4, 3 forms have dimension 4, and 4 forms have dimension 1. So this my vector space has functional dimension 10 of the functions on the manifold. Now this group G1, I think I call it G4. This G4. So this is diffeomorphisms. So this group has functional dimension 4, and this group has functional dimension 1. So the functional dimension of G4 is 5. So it's half of the dimension of P. So typically when you take the space and perform the symplectic quotient, which is precisely you get the space whose dimension is the dimension of the original space minus twice the dimension of the group. So it's 10 minus twice 5 twice would be 0. And that just means that there are no functional degrees of freedom. Unfortunately, there are moduli. And so this moduli space is an interesting moduli space, but it's very hard to study. It's essentially the cotangent bundle to the quotient of the space of 0 forms and 1 forms by the action of the group G4. And what does it mean? It means that so you study the space of pairs up to diffeomorphisms and up to the gauge oscillations. So what are the invariants of the section? These are basically the functions of this quotient space. Well, P modulo P plus d theta, we know these are gauge invariants. So for any closed loop on your manifold, this would be an invariant. But of course, this loop is also moved by the diffeomorphisms. So the invariants are kind of loop invariants on the form manifold. It's not they're not knots because loops are not knotted in form manifolds, but some kind of a so these invariants are provided by some kind of string functional space. So the holy grail of people trying to characterize QCD by loop equations. There are some local invariants one can write. For example, dp for dp times any function of s. So these are analogs of Heisenberg's. There are infinitely many of them, but they're kind of discrete. But there might be also many non-local ones. So this space most likely consists of components of various dimensions, probably finite or countable dimensions. And so the intersection theory may be defined on such manifolds. But of course, it's very far from being developed.
But are there any examples starting from easy M?
Well, I will, yes. So tomorrow I will explain that for at least for M, which is the product, this intersection problem will be equivalent to the Euler equations for compressible fluids I described earlier. So any solution, and there are many solutions we can find in textbooks, of course, will produce an intersection point on this manifold. Now, sometimes, so there is intersection theory, which I mentioned, so here I meant, when I was talking about intersections, I was talking about actual intersections. Now, there is a simpler version, which is what we use in algebraic geometry, where we count intersections with some weights. And if the intersections are not transversal, which is the case here, the intersection locus actually carries a certain structure, like abstraction bundle. And the simpler problem to study is to compute the Euler class of that bundle. So that would be an interesting kind of supersymmetric version of hydrodynamics, which people in hydrodynamics are not interested in, but I think mathematically, and I will argue tomorrow, string theory should be looking at. Then that would be a better defined problem. And so this is where the so the relation to Grassmannians which were mentioned come from interpreting intersections not literally but virtually. So you don't actually look for intersection points, but you count how many intersections are there, provided that you allow to deform the problem. Okay.
I have a very simple question, or not something I don't know, but what happens with this formalism if you consider fluid which is moving not in 4 dimensions?
Yes, interestingly, this setting, you see, you could say that, well, this is somehow still Baroque. Why do they take 0, 1, 3, 4? It looks like, I mean, if you come from the high energy physics community, this looks like a decomposition of some structure which comes from higher dimensions. And in fact, if time permits, I will explain that this is the most natural way of expressing this is in 5 dimensions, where this comes from a 1 form and comes from a 4 form in 5 dimensions. Certain features of this formalism survive in any space-time dimension. In fact, all space-time dimensions are easier for some reason than even ones. That would be, so 5 is a good example. And so then you don't even need this group if it works with differomorphisms. This is the most economical setting. You work in all space-time dimensions, and you formulate the equations in terms of the space of 1 forms and 2 n forms. Simply simplex manifold you can associate. So 1 forms are like they kind of dual to vector fields up to a twist. And so that's a very natural space you can associate to. Of course, if you reduce them down to 4 dimensions, you will have now many more components. So sometimes this can be interpreted as fluid with, as I said, with many component dye. So you have you want to paint the fluid different colors. Depending on how you reduce from, so if you go from high dimensions and you project to 4 dimensions, if your fiber is a group, you can have a spinning fluid. If it's
That's going to go to less than 4?
Yeah, but it's somehow it becomes less interesting. Yeah, so you lose. Yeah, you need degrees of freedom. So you go below. I mean, so I guess you could describe 2 + 1 dimensional dynamics in this way. It's 2 + 1 dimensional.
Thanks for questions, but you have another chance to ask them tomorrow.
I mean, one question which you could have asked is that if you go to any textbook or go to any talk, people talk about hydrodynamics these days, the first thing they start talking about stress tensor, what kind of terms you can get stress tensor, and that all the equations are just conservation of stress tensor, and I didn't mention stress tensor at all. So how come? So where is the stress tensor? So I will explain tomorrow.
Yeah, the religious extra terms of you can add to the stress tensor in the context of ADS safety or so. Like, what we
Yes,
say,
so we can discuss it
we can say how they follow through.
to some extent. Yes.
All right, so we meet tomorrow at 2:15. Once in which room?
Well, that will be disseminated.
Okay, good.
Probably through 24 hours.
In this corridor.
No.
Well, thanks. Okay.